In this lesson, we will look into convolutional neural networks. You're already familiar with the MNIST dataset, so it will be easier to describe a typical CNN. In our approach, which was simply feed-forward neural networks, we flattened the images into a vector of length 784. That way, however, we lost the spatial information of every pixel's neighborhood of pixels. For example, the 28th pixel and the 29th pixel in the vector we use are next to each other in the vector, right? Well, in the picture, they are actually quite far away. Furthermore, since we always start by taking a linear combination of the inputs, it will search for particular digits in particular places. For instance, a 7 written in the top left corner is very different from a 7 written in the bottom right corner. A convolutional neural network solves this problem by dealing with the original 28 by 28 photos without flattening them. Instead, it applies tiny, say 5 by 5 so-called kernels to every possible position of the image. Kernels are like weights. So, if we start from the top and continue down, we can count a total of 24 5 by 5 squares. The same applies if we go from the left to the right side. Therefore, the next layer is 24 by 24, which is the number of 5 by 5 submatrices. This is called convolution. The layer that we get is called a convolutional layer. The number of kernels you choose is a hyperparameter, and you are not restricted to a single kernel. Apart from convolution, there is another main step in CNNs: pooling. Most commonly, we would divide these 24 by 24 squares into multiple 2 by 2 squares without overlapping, and we'll take the largest number in the 2 by 2 matrix because we assume it is the strongest detail. That's how we reduce the dimensionality of the problem. What makes the issue slightly more complicated, though, is that most photos have colors, which implies that images have height and width, but also color or depth. This is a third dimension with 3 variables according to the RGB scheme: red, green, and blue. Thus, our original photo was not of shape 28 by 28, but rather 28 by 28 by 3. That's also where the whole tensor approach fits perfectly. So, the initial 28 by 28 matrix was not reduced to 24 by 24, but was actually converted in a 28 by 28 by 3 tensor, which was then reduced to a 24 by 24 by 3 plus tensor, depending on the number of kernels we chose to use. If we convolute and pool for long enough, we can reduce the dimensions to a vector containing one-hot encoded categories, like dog, cat, horse, and so on. In order to truly get CNNs, we need much more time than a couple of minutes. In general, though, to get the gist of it, CNNs are mainly used in image recognition due to their 2 major advantages. Spatial proximities are preserved. It matters where in the photo we find a certain detail. And a certain detail such as a human eye is looked for everywhere in the photo. Thus, a face can be recognized everywhere on the image. These 2 advantages make CNN's predictive power much higher than that of NNs, especially when it comes to image-related problems. Instances are robot vision, self-driving cars, Facebook tagging, and Apple's face recognition for unlocking the iPhone. A recent application of CNNs for a non-image-related problem was the Google Assistant technology developed by DeepMind. This is a competitor product to Siri, Alexa, and Cortana. Allegedly, they managed to apply CNNs in a way that converts artificial sound in a more human-like shape than ever. You can find the original announcement by DeepMind in the course resources. Alright, how likely is it that you'll use CNNs? Well, currently, image-related problems are mostly used by companies such as Google, Tesla, Apple, Microsoft, Amazon, and startups. The applications of CNN so far seem more or less out of reach for most people. That's the reason why we decided to focus our efforts on creating a comprehensive course with a focus on deep neural networks. That's a great value you can add to any company you work for, which CNNs don't really deliver, as they have a different focus. Okay, in the next lesson, we will make a quick overview of RNNs. Thanks for watching.